Hello, in this video I'm going to go through a question on power. And first of all, I'm just going to run through the question as you'd answer it. But then I'm going to look at one of the things that tends to confuse a lot of people around this particular type of question when you're looking at cranes lifting masses and things like that. Because I think there is a slight ambiguity in this, that the question fudges around an issue and it throws people at times. So, but first of all, let's just go through the question in a standard fashion. We've got a crane that's lifting a heavy object, so it's got a mass of 1500 kilograms. So it's already got that in the picture. It's raising it through a height of 25 meters, which is in the picture, but it's doing it at constant velocity of 1.6 meters per second. So it wants us to find, first of all, the tension in the lifting cable. So if it's moving at constant velocity, then according to Newton's laws, we've got that the tension in the cable must be equal to the weight, so that we've got no acceleration. There's no net force because it's moving at constant velocity. So we can just say that straight off, which means we've got a tension of 1500 G newtons. And then we can put in whatever we want for G, probably 9.8 or whatever. So that's covered the first bit. What's the time taken for the mass to be raised through a height of 25 meters? Well, if we're raising it through 25 meters, the time is going to be the distance divided by the velocity. 25 over 1.6 is 125 over 8, just changing that 1.6 into 8 over 5. So that is 15 and 5/8, which is 15.625. So just rounding that to a 15.6 seconds. So again, straightforward. We're just doing a basic velocity is distance over time calculation there. Right, now we're on to finding the rate of gain of potential energy of the mass. So this is the effective power output, because what we're trying to achieve is raising the mass. So this is our useful power output. We've gone through, so we're going to want MGH. Well, there's two different ways of calculating this. You've got the potential energy gain over time, and that is our wattage. So we've got, what was it, 1500 G multiplied by 25 divided by 125 over 8. So that would be a fifth, which would knock that down to 300 multiplied by 8. 2400 G, and that is in watts because we've got joules per second. We could have done the same thing of saying power is force times velocity, which is using the same numbers. You get exactly the same thing. Doesn't really matter which one you use. It's just two ways of describing exactly the same thing. So that is our rate of gain of potential energy of the mass. And not surprisingly, they've asked us here minimum output power of the motor. So the minimum output power is if we're assuming, minimum power of motor, that is assuming 100% efficiency, in which case our power in is power out, so it will be exactly the same. Therefore, the power of the motor, P motor, is going to be 2400 G watts. Of course, we're likely to need more than that because we're going to have losses. We're going to have friction and other such things kicking around. So that's a fairly straightforward question to go through. But there is an issue that I find a lot of people have with these questions. That So if you read the first part of this, so it's saying we've got a motor M in the crane lifting a total mass 1500 kilograms through a height of 25 meters. So say we just stop there. Now you say that to pretty much anybody, and what they imagine in their mind is initially the object is at rest, then it moves up through this 25 meters at some speed, and then it ends up at rest again. Because if you say to someone, oh yeah, I've lifted an object through a particular distance, you think, well, yeah, it started at rest and it's ended at rest. So this immediately starts throwing people off, thinking, well, we must have an acceleration at the start, we must have a deceleration at the finish, which means we've got these extra forces going on, and we have to take into account the change in kinetic energy, because in this space in the middle where we're actually lifting it, is the object has got a kinetic energy that it didn't have at the beginning because it was at rest. Now, all of those intuitions are good intuitions, and it's a shame that these questions are set up to say, well, actually, we're not using that scenario. We're assuming all the way through this that the object is already moving at 1.6 meters per second, and after it's moved 25 meters, it's still moving at 1.6 meters per second, which is nobody's interpretation of what the situation is. But it is, strictly speaking, what the question is telling us. So I don't like these questions for that reason, because I think they're just battling against people's natural scientific intuitions, which are good intuitions. They could have more sensibly a question where they're saying, right, well, I don't know, it takes 1 second in order to accelerate the object up to 1.6 meters per second, and then 1 second to decelerate it at the other end. And then we can start looking, well, what's happening in the acceleration? We need an extra, we'll be doing Newton's second law. We say, right, well, we need an extra amount of force in the cable in order to accelerate this object at 1.6 meters per second squared. So we're going to need an extra force, which is equal to 1500 times 1.6. That is going to be the net force that we're going to need, which is 2,400 newtons. So we need that extra force at the beginning in addition to this in order to accelerate it up to speed. So we've got those sort of calculations that people want to add into this question because of these good intuitions that they have, but they're not actually part of the question. So I suppose the end comment on all of this is, if you're one of those people who thinks that way when you're reading the question, don't think that you've got it wrong. You have my sympathy. I don't like these questions either. But all of this working out on the right-hand side is what the question is after. But maybe come up with your own version of the question and say, well, okay, well, let's have this. Let's have our 1 second acceleration and 1 second deceleration. Then look at our changes in force, the extra force at the start and the lower force at the end, the changes in the power, because the power at the beginning is going into a smaller increase in potential energy, but also an increase in kinetic energy. So see how the power might change for the motor at the start and at the finish. So yeah, there's a lot of things that you can do on this. So don't be afraid to explore around these questions and think, well, okay, I'm going to go off my reading of it and I'm going to do my own model in order to investigate what's happening to the motor here. So yeah, hopefully that clarifies some of the issues around questions of this type.